Okay, so it's time for optimization again. And last time we already introduced several information about constraint optimization. So today, April 30th. Today we're going to talk about something called Quadratic Programming, also known as Qp. Okay. Before we do that, we probably need to review some of the important knowledge about constraint optimization from last time. So let me grab my notes. Okay. So let's do a quick review. In today's introduction, we actually need to know things about linear programming and also Kkt conditions. We need to cover actually both. Okay, so let me do this. Yep. Let's review linear programming. You have done that in your homework, but let's review it. We should have a general format for linear programming. So no matter what kind of constraint optimization you have, you need to convert your problem into the following format. This is the standard format. Okay, this is a standard format. Okay, you have to convert all the inequality into equality, which means everything you have in your constraint needs to having the equal sign. You cannot handle larger than or smaller than. You can only handle equals to. And in order to convert those, you will need to put slack variables into your formulations. Okay, so this is just to remind you what we have introduced in the past. And often we rewrite that formulation in a vector form, so your problem become a much simple format if you write it down in a vector form. So this is how you visualize it in a vector format. Okay, and in the linear programming, we need to specify some portion of your variable as basic variables, and the others are non-basic. So in order to solve linear programming, we introduced how we could separate the problem into two portions. And the way we do it is like this. So we separate our variables into basics and non-basics. And when we are able to do that, we could later on start to go through our iteration process. So during the iteration process, we have in every iteration we have 2 steps. So which are the 2 steps? During iteration of linear programming, the first step is to check the coefficient of our objective function. So checking coefficients in objective function. Okay, so how do we do that? We basically utilize one equation, which is this one. Okay, and what you will get is a vector, and inside this vector, each component represents the coefficient for each is it basic or non-basic? The non-basic variables. So your non-basic variables. Okay? So you need to pick the most negative one. So that non-basic, which was 0, is to be converted to, hold on, yes, it was 0, converted to basic. So it's going to be positive later on. Okay, so that's our first step. Okay, and in the second step, and of course, if we cannot find any negative coefficients, that means we converge. So here, if no negative coefficient, that means converged. Okay. So if we have chosen one of the non-basic variable to be converted into basic, we are done for our first step. In our second step, we need to do the ratio test. So let's take a look. The ratio test. Okay, right here. So in the second step, we do a ratio test, and we need to calculate these matrix, and then when you calculate these, you will get also a vector, and in this vector you need to pick the smallest positive. So when you pick up the smallest positive, that means the representing basic variable, the representing, basic variable will be reduced to 0, and the rest of the basic is still not yet 0. If you still remember why we do this, this figure shows you why. This figure. When we did this example, we had 3 basic variables. They were positive, and our horizontal axis is our non-basic. We want to increase the value of the non-basic so it becomes positive. When we do that, these 3 basic will change its value. And in this case, x3 will reduce to 0 when x2 increase to 2. So this value 2 will be the smallest positive value that we found in our ratio test. That's why this variable x3 should be converted to 0. Okay, so if you still remember those or not, you could always come back to review what happened. Okay, so over here, when we chose the corresponding variable, so the corresponding basic variable will be converted to non-basic. So it was a positive value. After it's chosen to be non-basic, it will become 0. So that's how you could find 2 variables to swap with each other, and basic become non-basic, non-basic become basic. And then you continuously doing this until you cannot find any better solution. This is how LP was able to find the optimal solution. Okay? Now, a week later, we reviewed something called Kkt condition. So in Kkt conditions, we did a lot of derivations. At the end, we actually found we can only check several equations, and that will, if the problem was well defined and follow some of the assumptions, then Kkt condition will guarantee that solution is optimal. So let me see which are the Kkt equations. Here. So of course, in general, a problem looks like this. For Kkt condition, we are dealing with a problem, a general formulation like this. We could have any number of equality constraints. We could have any number of inequality constraints, but we can only have one objective function. Okay, if you have a lot of objective functions, you need to figure out a way to combine them together. Okay, so for a general formulation like this, the equations for Kkt conditions are given here. So these are the equations for Kkt condition. Over here, small n is the number of equality constraint. And small n is the number of inequality constraints. And over here, capital N is the number of variables. Okay, so just to avoid confusion, please make sure you know what does each number represent. Okay. So from here you could tell the number of mu. The number of mu. Lambda. The number of lambda equals to the number of your equality constraint. So you have I goes from 1 to n, right? And the number of your mu basically is the same number of your inequality constraint. So your summation goes from 1 to n. Okay? So these are the review of what we have done in the past 2 weeks. How about today? Today we're going to talk about Qp, quadratic programming. So when we are dealing with quadratic programming, what does it mean? What's the difference between LP? So basically we introduce a little nonlinearity into the problem. So we allow the formulation to handle some nonlinear information of the problem, but we only upgrade the order by 1. Originally, we are dealing with linear problems. Now we are dealing with quadratic problems. So let's say if the problem is 3rd order, 4th order, or even higher order, we still only handle 2nd order in Qp. So what can we do? We can do 2nd order Taylor expansion. So no matter what order the problem it is, you could always do quadratic Taylor expansion. Okay, so after 2nd order Taylor expansion, if it's necessary, if necessary. So if the problem by itself follows the format, you don't need to do Taylor expansion. But if the problem is actually in a higher order, then you need to do a 2nd order Taylor expansion. Then you could rewrite the entire problem into the following format. You basically minimize your objective function. Over here, we are writing in this way. How about the constraint? I will explain about those details later on. The constraints basically and how about equality constraints? And all the x are positive. Okay, so probably you feel like you have never seen this equation before, but actually it's a very standard format related to 2nd order Taylor expansion. Over here, H basically is our Hessian equation, Hessian matrix, right? you already know about the Hessian when we introduce the Newton's method. Okay? How about C? C basically will be your gradient. Basically is the gradient vector. So basically it's the gradient vector. Okay, because in your Taylor expansion, the coefficient for your first order term basically is gradient, right? But how about the constant term? So in Taylor expansion, you should have a lot of constant terms. Where are those constant terms? We don't need them. Okay, so why no constant terms? Because when you complete a Taylor expansion, those constant terms are just constant. When you start with an initial guess, the value of the constant will be the same after you complete the optimization because they're constant. They don't change with your position of variable. So the optimization actually does nothing to the constant. Okay, so in fact, when you do optimization, if there's a constant term in your objective function, the constant term doesn't change the solution. You don't actually need to handle it. You can just get rid of it. Okay? So that's why there's no constant term. And for the constraint, from here you can tell both equality and inequality, they are still linear constraints. So, in fact, quadratic programming can only handle quadratic terms in objective function. The constraints are still linear. So if you have nonlinear constraint, you have to do first order Taylor expansion in order to do quadratic programming. So use first order Taylor expansion. If necessary. So if the problem originally is having a or several nonlinear constraints, you need to do first order Taylor expansion to get linear constraints. Otherwise, quadratic programming cannot handle those. Okay, so that's the limitation of Qp. We handle second order objective and first order constraints. Okay, so this is a standard format. And let's quickly review the first equation in Kkt condition. The first equation in Kkt. What does it look like? It's basically gradient of f plus some coefficient multiply gradient of h plus some coefficient multiply gradient of g. Okay, so this is the first equation. So it looks like this: gradient f plus some vector. Let me think how I should. I think it's fine if it's actually a vector multiplying the gradient of h plus mu vector multiplying gradient of g, and this must be 0. This is the first equation in Kkt. Okay, so actually, there's a certain type of analysis that is exactly fitting what we're doing here, and that equation is called Laplacian. So this is the first time I introduce this new terminology. So you heard of Laplace in many other subject and mathematics, and Laplace, I'm not even sure which Laplace. Laplace, one of the Laplace, or the Laplace, I'm not sure. Laplace did something over here when we do this is so-called the sensitivity analysis, because whenever we are checking the gradient, we are checking the sensitivity of functions. So there's a way of formulating this equation is so-called the Laplacian. So we usually just write Laplacian L equals to F plus lambda times H plus mu times G. And over here, I should have a vector of lambda and I have a vector of H. So those are vector. Okay, so it's like a dot product between a vector of lambda and a vector of my H functions. So I have a vector of H functions. And then the last term is a vector of mu, and dot product with a vector of all the constraints. So this way of combining objective function and all the constraints, we call this Laplacian. And why do we like to formulate this Laplacian? Because the first equation of Kkt is basically gradient of Laplacian equals to 0. If you compare the definition of Laplacian and the first equation of Kkt, you can tell actually the first equation of Kkt is Laplacian, gradient of Laplacian equals to 0. So this is basically the same as this guy. Okay? But in our general formulation here, if we only do this, this is not the complete format of our Laplacian, because this one is missing in the this derivation at the bottom. Okay, so we didn't consider the ones of x must be larger than 0. We didn't introduce those in the derivation at the bottom. So to be correct, when we try to formulate this gradient Laplacian equals to 0, we actually need to also consider the last constraint right here. Okay, so now I'm going to write down the complete formulation of Laplacian, and then we should start from there. So the correct formulation of Laplacian for the general problem. Which general problem? This one. Okay, should be written as Laplacian equals to f plus because there are gonna be a bunch of constants. So if I use lambda mu, and I need a new Greek symbol for a new term, so there will be a lot of Greek symbols, but there will be too many. So let's change the Greek symbol to English characters, so that later on our formulation will look nicer and also match my notes. Yeah, so in my notes, actually what I did was u dot g plus v dot h plus w dot, so over here I have negative x, because in general we are handling the ones smaller than 0. So because our x must be positive, so we could convert this into negative x must be smaller than 0. So those negative x are just like several more g functions. So we should handle them exactly like the g functions here. So so it's just like we put this negative x into our Laplacian in the way that we usually do. So we we need to make sure the constraint looks like the format where the smaller sign is shown. It's not the larger than sign, it's a smaller than. And then on the left hand side of that will be basically the g, and it will be directly placed in our Laplacian. Okay, so that would be the complete formulation of Laplacian for this general problem. So since we would like to analyze, we like to get gradient Laplacian equals to 0. So let's take a look what will happen if we want to do that. So now let's do gradient Laplacian. So the gradient Laplacian, of course, will look like this. And over here I should have minus w. And we wish this equals to 0, right? And we could actually directly derive all the gradient terms. We could go ahead and derive those. And to do that, we could review what we had over here. So we can put them here to remind us what are our functions. Okay, these are our functions. So if I do gradient of f, I should have Hessian dot product x plus c vector. So that should be our first order derivative of f. Okay, plus u still the same. How about the gradient of g? Over here you actually will have capital A, but when we do dot product between two vectors, we could reverse the order. But when we do dot product between a vector and a matrix, in fact, we could reverse the order as well. And usually when we like to do dot product between a matrix and a vector, we like to see the matrix stay in the front. So over here, we just write it down in the order that we usually like. So we would like to write this term in this orientation, so that when you later on when you do multiplication, it doesn't look weird. Okay. Similarly, for our gradient h, I should have n times v, and for w still the same, and we wish this to be 0. Okay. So this is first equation that we have for quadratic programming. Okay, a bunch of constants h, c, a, n, and w. They are constants. Okay, and a bunch of variables in there. X, u, and v, and w. They are variables. So x still variable. U, v, w. They are called the Laplacian multipliers. Laplacian multipliers. And they are still, right now they are still unknown. Okay? We don't know them yet. We just know we have those coefficients in front of our constraint functions, but we don't know what's the value. Okay? So that would be the first equation that we have for Qp. Next, also based on Kkt condition. And this time we are studying the second equation in Kkt. So what would be that? The second one is the coefficient in front of g multiplied g must be 0. So mu g equals to 0. And we should do that as well in Qp. So how about what's the coefficient in front of g? Basically u dot product g equals to 0. Okay, and also we have our w. W is also our inequality constraint. So don't forget about that one. This guy here. Copy. Paste. Don't forget about this one. So the coefficient in front of the last one should be w times negative x. This also must be 0. Okay? And this is the second equation in Kkt. How about the third equation? In Kkt. The third equation in Kkt tells us all the mu must be positive. Okay? So what are the mu's? So basically, u positive and w positive. Okay, these are the conditions. Okay? So let's see what we can do. We can play with this one. U dot product g. What is g? G is a x minus b. Okay? And this guy must be 0. Okay, so we have a bunch of equations right here, and let's stop right here and then continue to the rest. So how about v? Did we have any rules about v? So basically mu. How about the rules of mu? Okay. Mu cannot be 0 actually. How come mu cannot be 0? Because when we do Laplacian, it's important that the gradient of f is a linear combination of gradient of h and gradient of g. So if the coefficients in front are 0, that means if all of them are 0, then you're basically telling us gradient f equals to 0. But in unconstrained optimization, this rule is okay. We of course would like to find a position where the gradient of f equals to 0. That means that's the very bottom of the f function. But if our Laplacian multiplier are 0, that means our constraint doesn't play a role in finding the optimal. So it's like you are treating the unconstrained problem. You are treating the constraint optimization as unconstrained optimization. It's like you ignore those constraints. So usually your lambda shouldn't be 0. Your lambda shouldn't be 0. Otherwise, it's like you are ignoring all the constraints. So based on that idea, you can tell, how about v? V should not be 0. Because they are the coefficients in front of the equality constraints. The coefficients in front of equality constraints. Okay, so it's like we have something, we follow Kkt and then derive several equations. Now we can see that the way Qp is trying to solve a quadratic problem actually is trying to convert everything into LP. So when we handle this problem and we realize there's something that is not following the general format of LP. So that one is basically the inequality. Remember, when we solve for LP, we need to convert everything into equality constraint. So for the next step, we start to moving forward and try to reformulate Qp into a LP problem. So the first thing we need to handle basically is to convert everything into equality. Okay, so our g functions now becomes equality by adding some slack variables. But remember, when we do that, our slack variables should be positive. Okay, so S right now, right here, basically is our select variable. Okay, so when we do that, we were able to convert all the inequality into equality. So that's quite important for quadratic programming. Okay. And we need to do, let me see what else. But when we do that, we found there's still something that we don't like. Which one? Basically, this one. Because your select variable must be positive. The s must be larger than 0 itself is actually inequality. So there's a way to convert this one, this small equation, into equality. So how do we do that? It's a quite unique way. So next is to convert s larger than 0 to equality. So we define something called, let me see. Can we define that? Hold on. Let me just double check. We define v equals to y minus z and cannot be 0. Because in the earlier we said this one cannot be 0. Okay, this one. Right? And we also sorry. The reason why we did this is not because we want to convert. This was not the reason. Okay. So but this one we want. Okay. Why do we do that? Because to handle this guy. So let me actually erase off this one. Sorry. And then start to talk about. So basically we have a bunch of equations. We need to handle them one by one. And for this one, we define v equals to y minus z. Okay? So y and z are just two different vectors. But we just say, okay, v equals to y minus z. So two new vectors. And we want to make sure y and z, they are both positive. Okay? And we wish this doesn't equals to 0. Okay? Why do we do that? Because the original description is like v is not 0, but there's no exact equation to define what is v. You just have a concept knowing v cannot be 0, but we need some equation to represent that. So v could be any number y minus z. As long as y doesn't equals to z, then v won't be 0. So that's why we define those to express v cannot be 0. Okay? So the box, the equations in the box will be the equations that will be utilized later on. Let me see what else. These will be considered later on. And also this one. And since we already introduced our select variable, we can tell the select variable, or we could say ax minus b equals to negative s. So we can actually plug into one of the equation on the top right here. So we have u dot product minus s equals to 0. And that one is like a shorter version of what we had earlier. Okay, so basically all the equations has been rearranged and then being rewritten into a new formulation. Now can we put them together and see what we have so far? So everything together, I think I copy it and then paste them here. So this is the first equation we have. Okay. Double check if I have the exact one. Yes. But over here, one thing could be expand, which is v, because we know v equals to y minus z. So this one we change to y minus z. Okay? And we keep everything the same. We keep the rest the same. And how about the other one? I want this one. Okay. Okay. The next one I would like to get the one that we originally have. So actually, we never talk about h here. We never talk about it because it's following the general format of linear programming. So we never rewrite it. But now we would like to also take it to the next page. Paste it here. And let me get rid of a lot of stuff. Okay. Okay. The next one I would like to take is this one. Okay. And when we take it here, we could actually remove the negative sign because it doesn't change anything. Okay. So Wx equals 0. And the next one we should take us equals to 0. So over here, oops. Yep. So what are the rest? We already have those. So the rest are just basically, we don't need this. We basically have a bunch of variables larger than 0. Right? So S should be positive, Y and Z should be positive. And what else? In this original problem, we have oh, I think I accidentally removed this guy. Copy it. Paste. So U and W, they should be should be positive, right? And at the beginning, we know X is positive. At the beginning, we already know X is positive. So we have U, W, X, S, Y, and Z. They are all positive. Okay, so it's like a bunch of new equations when we did all those derivations. And over here, you can tell the first three, they are linear. They're linear functions. They're just a bunch of coefficients multiplying our variables. So what are our variables right now? These are our variables. S, Y, Z, U, W, and X. These are our variables. Okay? And the first three equations are linear equations of those variables. And how about the other two? The other two are nonlinear because they are we don't need a negative sign here. We don't need this because it doesn't change anything. So these are the product of two variables, and they must be 0. Okay? That's fine. At least we are moving forward from our original problem. Our original problem was having quadratic formulation in the objective. But when we convert everything into this, we have no more quadratic form. The only nonlinear term are the two equations that we have. So by Kkt condition, we are able to rewrite this complicated problem into some new equations. Okay, so this looks messy. Can we make this entire derivation cleaner? Actually, we can rewrite this whole thing into a matrix form. So let's take a look. And over here we have our X, U, W, S, Y, and Z equals to. We can try to rewrite what we had earlier into the following matrix form. Let's write down the second one first. So the second one, basically, you have A transpose here. Because A times B, right? A dot product B minus B. B is a vector of constant. So that basically is your constant on the right-hand side of your matrix, and you have plus S. So S is the fourth one, so here you should have 1 right here, and the rest are just 0. Okay. Of course, S is a vector. So the 1 right here is actually a vector of 1. If you have 5S, the 1 here, you actually have 5, 1. Because when you do dot product, in front of each S, you should have a coefficient of 1. Yes. So this is just a very simplified format for you to visualize the whole thing. But you still need to, whenever we put something inside the box, you need to make sure when you multiply one thing with each other, the order matches. Okay. So let's continue. The second row, let's handle the third equation right here. So I should have n transpose here, because multiply with x, and then no more. On the left hand side, we don't have anything else. But on the right hand side, I have a vector of e. That would be another vector of the coefficient. For the last row, I'm going to handle the first equation right here. I have Hessian. I'm sorry. I don't need transpose. Because when you have matrix multiplying a vector, you don't need transpose. So that was wrong. You don't need transpose. So just H multiply, A multiply, N multiply. Yeah. And then the second term, I should have I have a C right there. So C is like a constant. I move it to the right hand side. So I have a negative C over there. And about the U, in front of U, I have a A matrix. And in front of Y, I have a N matrix. So N matrix here. In front of Z, I should have negative N. In front of W, I have negative 1. Okay. Yeah. So it's like we could rewrite the entire everything above, the three linear equations above, into this format, and it helps you to formulate these three equations easier, and also easier for computer programming. Okay. And once we have this, let's rename those those matrix into the following format. Over here, we call this capital B, matrix of capital B. And over here, let's call this capital X. It should be a vector. And let's call this capital D. Should be a vector. Okay? So for further derivation, we are going to just use super capital B times this capital X equals to capital D. So that will cover the first linear equations in Qp. Okay? So let's put them together. Once we have this, we put everything together. We now have capital B times this capital X, minus capital D equals to 0. And what else do we have? Everything inside this capital X should be positive, right? Because those are our variables. So everything inside this capital X, they are positive. And what else? We are missing the 2 in nonlinear constraints right here, so we cannot forget about them. So copy them and paste them here. So now our formulation become simpler and simpler. Okay. If we can find some solution for this that satisfies everything, it's like you have a solution point that is following the Kkt conditions for the original quadratic problem, right? So you just need to find a point that satisfying everything here. So a point that satisfies the above equations basically satisfies the Kkt conditions of the original quadratic problem. So the goal of the following step basically is trying to find a point that satisfies everything. Okay? So how do we do that? Now when I see this, I feel like mathematicians are really smart. So some mathematician came up with a way to find a point that satisfies the above equation. And that's the magic of Qp. Deriving those are just like deriving equations, but it's not helping us to find the optimal yet. But the following step truly help us to find the optimal. So the following step is to formulate a new problem. So when we formulate this new problem, what do? We minimize let me write as a summation of capital Y. And I will tell you what is capital Y. Capital Y is maybe let's not use capital Y because we had variables called Y. So let's use what symbol we didn't use. A, B, C, D, E. We had E, F, G, H, I, J. We have never used K before. Yes, let's use a bunch of capital K. So what does K mean? K means K1 plus K2 plus blah, blah, blah. A lot of Ks, okay? So subject to what? Subject to capital B, dot product capital X minus capital D. And over here, let's say we have a plus of, so in fact, there's only 3 of them. Do we have only 3 of them? Let me see. Because we only have, not maybe we have a lot because we don't know the length of B, E, and C. So vector of D could have a very long length. So we don't know what's the length of K. So basically a bunch of k. And we put y here. Okay? And make it equals to 0. Oh, not y. K. We put all the k here. So k keeps all the numbers of small k. K1 to right here I can put a number, maybe km. And n is the number of or same length of d. Because the order must match, right? And what else? All the x must be positive, and also all the k must be positive. Okay. So this is a solvable problem by LP. Right? Because we only have equality constraint, and all the variables, they are positive, and we have a linear constraint. Okay? So if we are able to find an optimal solution, of course we wish all the k become 0, because if all the k are 0, that basically is the minimum you can get, because all the k should be positive. If every k are 0, then obviously that's the optimal. So we can use LP to continue solve for the solution until we find a set of solution where all the k are 0. So we will try to find a set of solution where k becomes 0. So that basically is the optimal. Okay? So when k equals to 0, what does that mean? That means your x at the moment satisfies this equation. Because over here, in this new problem, if you find a set of solution where your k is 0, then bx minus d equals to 0. And that basically is satisfying what we had earlier at the beginning of Qp. Okay, so this is like it's not like a direct way to find the solution that satisfies those constraints, but it's a very intelligent way for you to find a point that satisfies the first equation in these rules, and the procedure could be using LP, because the new formulation that you created is a solvable problem by LP. So the problem was uniquely being reformulated into the current formulation, and then a new problem was generated, becoming solvable for LP. Then using LP to find an optimal point where all the k becomes 0, and whenever your k becomes 0, the rest of the x will satisfy this equation, meaning satisfying the first equation right there. Okay? So once you are able to do that, of course, the second equation is also automatically satisfying. But how about the other two? How about the other two? So So then we can go back and check if those two nonlinear constraints could be satisfied. So the final step, once you are able to complete everything, the final step is to do this. So the final step is to check these two equations. But of course, it's possible that your solution doesn't satisfy those. It's very possible. So if satisfied, then congratulations, you have found the optimal solution of the original problem. Okay? But what if it's not satisfied? What if it's not satisfied? Then we cannot guarantee the solution is the optimal. Since when we start from the very beginning of the problem, we use a lot of approximations. We use Taylor expansion. So maybe it's okay if we stop right here, although we know the solution may not be the true solution. But it's already a pretty good solution. It already satisfies several constraints, not yet all the constraints. So probably we can move on to a next iteration, redoing all the approximations and try to do something over there. So at this stage, Qp cannot guarantee the solution is the true solution. It can only tell you, okay, it's satisfying the first two equations right there, but it cannot satisfy the third and the fourth. So at this point, Qp doesn't help. But you could always move on to this new position and then try to do the same procedure again, see if you can become luckier. Okay? So if not, it's not satisfying, so it's not the true solution. Or you can say not the optimal. Okay. So that's the only thing you can say. So there's some method called sequential quadratic programming. Sequential quadratic programming. It's basically following this kind of concept, the famous SQP. Okay, so what does it do? This is like a original problem. And it's having nonlinear objective function, and also nonlinear GNH. So a very general problem could having nonlinear f and also nonlinear GNH. So what does Qp do? They use a second order Taylor expansion and use a first order Taylor expansion, and then we formulate linearized problems. So but our f is quadratic, so let me just put f hat to represent quadratic. Okay. And you have G bar and H bar representing linear. So you basically have approximations of your original problem. So this is good for, this is like a Qp formulation. Okay? And then what you did a lot of stuff. You formulate the four equations here by everything that we have done today. So basically you did all these, you derive a bunch of stuff, and you get these four rules. Okay, you want to satisfy it. But you have to figure out a way to find those equations. So you want to satisfy all these rules. Okay? Maybe I do these in the next page. Let me just cut it and then paste it here. Okay, so you want to satisfy all these rules. And what do you do next? You formulate a new problem. You formulate what? You formulate this. So you formulate this, and this is solvable by LP. Okay, and then you will try to find the solution and see if that satisfy. You will do once you finish this LP process, you will check convergence. And what do you check? You basically check all those equations when you when k equals to 0 and you pass all the x to your check, right? Because when k equals to 0, you get a bunch of points, a bunch of solutions that may satisfy your first two equations, right? But you need to also check the bottom two. So if converged, if yes, you get optimal. But when you get optimal, it's actually the optimal based on your approximation. So remember, you did several approximations here. So your optimal is the optimal based on these approximations. Okay, so even you get optimal at the end of this whole thing, it's still a optimal based on those approximations. It's the optimal of the Qp formulation. It may not be the optimal of the true original problem. Okay, so let's just stop at the case if you converge. How about when you have a convergence check and you actually couldn't find the optimal? So what if the situation is no, it doesn't satisfy, so it's not optimal. So no matter if you have a optimal solution or not optimal, you still need to start over again, because your problem starts with a bunch of approximations. So no matter if you have optimal or not, you still is not getting the true solution. So the most important thing is you iterate. You still need to do, so you should go back to approximation. So it's like you are re-approximating the problem at the new point. Okay? So when can you stop? When you get the optimal, when can you stop? When you already get the optimal and your optimal solution of this iteration is the same as the optimal of your previous iteration, then you are very, very sure is the optimal of your original problem. Right? So this is how, of course, the way this is sequentially iterating could be modified in many different ways, but this is one way. Okay? And usually if you are working on like research about optimization, this is where you can start to be creative. You can introduce a new way of converging, of iteration and convergence. You can maybe set up different rules to speed up the process. But the standard derivation of Qp is like this. We have an original problem. We have approximations to get a Qp formulation where we have quadratic objective and linear constraints. Then we derive a bunch of equations based on Kkt. So this is based on Kkt. We derive a bunch of equations, and then we try to simplify them so that we don't have too many equations. And once we have that, we formulate this additional problem. It's like a dual problem. And by finding the solution point for that additional problem, we could find possible candidates for the optimal solution. Okay, so this is the Qp and SQP. Okay, in your in the exam, I will not ask you to do anything about Qp. So this is just something for you to know. And even I would like to ask you to do something in the exam about Qp. I think it's already is too much because too many calculations. So remember last time at the end of last time I tried to write a computer code to show you how the homework looked like, and at the time I used something called fmincon in MATLAB. So actually fmincon is a optimization toolbox that is mostly based on SQP. But does it always use SQP? No. So in MATLAB fmincon, it will actually do a lot of kind of checking inside its iteration procedure. So the toolbox itself will switch from different methods based on the check. So what I'm introducing today is just like a fundamental of SQP. That doesn't, we don't really need to solve SQP in this way. So in MATLAB, they already optimize their code. So whenever they feel like, okay, this problem cannot be solved in this way, they will automatically switch to some other solver and then try to find solution for you. So actually, fmincon is quite useful for finding optimal because they help you to find the optimal solution using their most preferred solver. So let me share some experience with you about how I work with fmincon and how I can publish papers based on this. So let me, in order to do that, I may need to switch my screen to the other mode. Hold on. So I don't need to show you my iPad anymore, but I would like to show you something else. I would like to show you the entire screen. Yes. Okay, this is fine. And I will stop showing myself, otherwise you see 1,000 of me. So stop this and it's impossible to broadcast this and also show it on the screen because I always capture the same thing and then right. What do I do? If I open a window, you see what? You see 1,000 of those. Oh, how about if I maximize? What do you see? Because I'm capturing the monitor and then I'm showing it on the screen. So you see too many of them. So I should visualize this in my iPad. Yes. So I should go back to the original way. Just use the iPad. So everyone can see it here, and also I can broadcast properly. Okay, so just show the iPad. Let me just see Dropbox. What time is it? 4:12. So this, let me just share with you some of my previous experience of FMinCon, and then I'm done for today. Very slow internet. Oh, because I didn't. Okay, hold on. Need to connect to internet. Let me try another trick. I'm not sure if it works. No, it doesn't work. I need internet. Or what can I do? I could use this one and then throw it to my iPad. Hold on. So let me just show you something that I have done very long time ago. This one. Maybe another one. Hold on, give me 1 second. See if I can use AirDrop to drop it to my iPad so you can see it. AirDrop. Turn on Bluetooth. Do I see myself? Okay, I see my iPad, and let me see if I can drop it here. Okay, I should be able to open it like this. No, I need to get online in order to see it. Let me try something else. Let me try Slides. Google Slides. I need to sign in. Okay, let me try something else. Let me see if I can find a internetless solution. So Keynote. Continue. Importing. Done. Okay. You need to see it here. So this is 2008. Probably the first presentation I did when I was a PhD student, like an international conference. So what did I do? I had two advisors. So Yogesh Jaluria was our chairman in Rutgers, and Haichang Jia is my co-advisor. So Professor Jaluria, he's from India, and he was our chairman. Professor Jia was from Taiwan. So I had two two advisors. And Professor Jaluria was in the thermal field. Professor Jha was in design field. So I was always a multidisciplinary guy. So I basically work with many different research fields. Okay. So what was I doing? I was doing CVD. So you must have heard CVD in the past. It's a semiconductor process, and it helps you to deposit chemicals on top of something. And I was working on a kind of CVD reactor, the vertical type, where you have some chemicals coming from the top, and at the bottom you have heating. Because of the heating, the chemical reaction happen at the bottom. So some product came out and deposit at the bottom, and the rest of the reactant go out, leave the chamber. So we are doing this, advised by my Indian professor. So that was the CVD I did. We were depositing silicon on top of the bottom surface. So silane came from the top with hydrogen. At the bottom, because of the heat, silane become silicon, and hydrogen went out from the side. So we were doing simulation. So if any of you are from the thermal field, you probably heard of Fluent. It's a CFD software. At the moment, it was not with ANSYS. Fluent was by itself. So several years later, ANSYS purchased Fluent. So now Fluent is inside Workbench. You can use ANSYS to do this. But at the time, Fluent is by itself. So this is the boundary condition for that simulation. Once you did it, you can see the streamline on the top. Color represent the velocity. At the bottom, you can see the temperature distribution. And you can also see how silicon deposit. So because we can study the deposition rate, and we can tell how silicon will be deposited at the bottom of the surface. See if that's uniform. So it's a very thermal problem, but how can we use optimization in here? So basically, we don't know what's the ideal velocity of silane. We don't know what's the ideal temperature at the bottom, so that we can have fast production and also uniform production. So the goal was to have speed and uniformity at the same time. So I think we did a bunch of analysis, and the simulation said the deposition could have many arbitrary shapes. So we did a lot of analysis, and then we have something like this. So what's this? At the left lower corner, you see a curve. We call this response surface. So it's like have you heard of linear regression? So this is nonlinear regression. And we did, for example, 100 tests. Then in the solution space or the function space, we should have a bunch of function points. But we don't know what's the value between every testing. So we use a regression tool to connect all the experimental points. So that's why it's a regression method. And from here you can tell the left lower axis, it was temperature. The right lower corner, it was velocity. So I was changing the temperature and the velocity. So I was changing them. I can have a bunch of combinations of these two variables. And the vertical axis is my response. So I have something that interests me from the numerical simulation, and I analyze every response from every test and then formulate this curve. Okay? So from here, if you are not clear, I can explain on the board. But whoever is broadcasting, seeing on Facebook may not. Maybe I can do it here. So you have a 2D axis. You can have your first variable, you can have your second variable, and as an engineer, you must know what's DOE, design of experiments. Basically, you design different levels of your X, different levels of your X2, and then you have a bunch of combinations. You could test all the combinations, or you could just test some of them. So let's say you decided to test 4 levels here and 4 levels there. Then you have 16 possible combinations. So you could design your experiments and then ask Fluent to solve for these 16 combinations. Or if you are doing experiments, you are not a simulation guy, you are a experimental guy. You could test all 16, right? And once you finish your simulation or experiment, you could figure out some factor that interests you. So some F could be here. And in every experiment, you could have some results based on that combination. You have a bunch of them. So what I did was I tried to connect everything. And then I get this we call response surface. To get this has nothing to do with optimization. But if I have this, I have functions. So this response surface basically is my f of x1 and x2 inside this domain. If I have equations, I can do optimization. If I don't have equations, I only have 16 points. So usually, if you don't know optimization, you will have 4x4 experiments. And sometimes you will do Taguchi sensitivity analysis, or sometimes you will just, I don't know, pick up the best one within 16, right? That's too easy, too boring. In your thesis, you have 100 pages. If you only do that, they only give you 10 pages. You need something to give you 30 pages, right? That's why you need to do analysis. That gives you 50 pages. So I did this to get like a very smooth, nonlinear equation of the response. If you are interested, I can tell you more about this later on, but not today. So let's say we have the equations like that, the response surface like that. So I'm not only interested in one thing, I'm interested in 4 different things. So in each Fluent simulation, I get 4 values. So I could formulate 4 equations. And usually, you would like to maximize some of those. You would like to minimize some of those. You can make up a story like this. You can make up stories. You can say, oh, let's maximize what is MDR. I think it's the deposition rate. You can say, oh, let's try to maximize the deposition rate such that, subject to what? The certain constraints must satisfy certain rules. So you can make up your own formulations, and then, of course, they should be meaningful to your application. And then you can try to see what would be the solution. Okay? So the first equation I put into this problem was the deposition rate. It looks like this. And supposedly, I would like to have maximum deposition rate. So if you only have one response like this, your thesis is very boring. Because you don't need to do optimization. This is your solution. Your sister can optimize it for you. So it's too boring. We cannot stop right there. We need to make it interesting. So, like I said earlier, I not only want to have the maximum speed of my production, I want uniformity. So in my Fluent, I have a deposition profile. I analyze the uniformity, make it a number. So for every experiment, I have a number representing uniformity. So RMS is the root mean square error. KUR is so-called the kurtosis. Kurtosis is like a statistical analysis representing the profile. Basically, if it's too large, the uniformity is bad. Okay? So that's why I said the root mean square and kurtosis has to be smaller than some limit. If it's too large, it's not uniform. If they are within a range, it's reasonably uniform. Okay, so then I apply my second function. My second function looks like a mountain. Okay, looks like a mountain. And then I set up some limit. So my value must be smaller than this cut. So whenever my solution is not at the peak of this mountain, it's like the bottom side of the mountain, I'm okay. So I use MATLAB to draw that region of the mountain area. And those areas basically are representing the infeasible space, right? Because we don't want to go there. And I study the kurtosis. So the kurtosis looks like a beach, right? This is like ocean. This is like on the side of the beach. So I also plot out the infeasible area of that kurtosis function. So for this case, I need to find the optimal within the white area, because only the white area satisfying all the constraints. And what did I do? Then I use MATLAB. I basically plug in all those equations into MATLAB and just use fmincom to solve it. So when I do this, I didn't actually spend time on the derivation of SQP. I didn't try to create a new method. Because when we are doing this research, optimization was just a tool. Okay, you just need to know how you could relate your original problem into an interesting problem. Okay? And at the end, we actually found several solutions. This one is the best one. No, this one actually is the best. So because this is a very nonlinear problem, we have too many solutions. Okay. And this is like a different formulation. And in this case, the best one is good. So that was how I utilized the fmincom. Okay. Can we take a break? What time is it? 4:30. Actually, that's everything I want to cover today. I think I will use some other time to show you how to use fmincom. Okay. So, and we don't have homework for today. Let me use the bathroom, and then I come back and talk about exam. Okay? So you can take it.